So let me deal with some of these challenges as we have learned on them. So the first point is how to contact individual junctions at all. So this is a point to illustrate. We tried to contact them by tips in using nanomanipulators in the scanning electron microscope. These are quite sharp needles, not the best what you can get, but close. And you see that the radial junctions are really very, very small. So actually the AFM, which has very sharp cantilevers, is better for that. But our traditional approach using the conductive AFM was not very successful. The conductive AFM is typically done in contact mode. So you scan your tip through your sample, and actually the radial junctions are not strong enough, and they will not stand the few tens or hundreds of nanonewtons which are there as an applied force, and they will move away. And so if you look at the maps, this is the topography map and the local conductivity map, and we see a very hazy images, and that's due to the movement of the radial junctions. I must say that this picture is used to illustrate the point, so it's a very bad picture. We can do better than that if we use very low applied forces of, say, this was about 20 nanonewtons. Then we have much better images in topography, but we don't get very good images in the local current, and that is, if you have low applied force, you don't define your contact very well. Fortunately, we are able to use a relatively new mode, the mode which is called peak force mode. And peak force mode is something like a dynamic microscopy. So at each point, your cantilever is actually approaching the sample, and during the approach, you measure the force between the cantilever and the sample, and you can have a feedback fast enough so that if your force gets close to the value which you want, you can stop the approach, do the measurement, and then withdraw again. And in this case, we were able to measure the topography of the nanowire junctions quite nicely. This is the three-dimensional representation of the topography, and you see the individual nanowires. You also see strange shape. The shape is pyramidal, but this is not the shape of the junctions. This is actually the shape of the tip, because now we have a convolution of the tip geometry and the junction geometry over each other. We can measure the topography for the samples which are without the top TCO and with the top TCO. We can measure the diameter of the junctions, which would be about 300 nanometers without the top TCO and about 600 with the top. And this is still not very nice if you compare to the image which you get from SEM. So if you have an SEM, you get many more details. Comparing with the same AFM images as we had before, you can get much more details here. And actually there is another point, and that is, if you use AFM, you cannot go down to the bottom. You cannot reach the space in between the nanowires. We try to use very sharp cantilevers to go in between. You can, but still not completely down to the bottom part of the junction, and that would be interesting to measure as well. But the advantage of the AFM is that you have the context to the sample, so you can measure both mechanical properties and electrical properties. To illustrate the mechanical properties, I just add the adhesion and peak force error signals. So now we see quite nicely the details on the surface structure of the junctions, but we are mostly interested in the maps of local conductivity. So this is a picture of the 5 by 5 micrometer square field of view, and we see the height image and we see the local conductivity image. I should point out that we usually use the negative bias applied to the sample. This is to avoid the local anodic oxidation, and that means also our currents are negative in the image mostly. So the scale is from 0 to -7 picoamp. So the more conductive areas are the ones which are dark in this image, and most of the sample is actually with low conductivity. you can look at the correlation of the topography and conductivity image. So you see that there are some conductive areas here and here, or here and here. They are different because this is conductive and there is a depression here. This is conductive and there is a nanowire there. So to correlate those images, you can overlay them on each other. So this is a 3D image of the topography and conductivity together. And you see some of the nanowires are more conductive and some of them are less conductive. Which are the better? We think that the ones which are better are the ones which are low conductivity, because the bias on this sample is actually now in reverse bias of the junction. So we should see the diodes with low conductivity, and those should be good. You can do further evaluation of the conductivity maps. So we enhanced contrast, and we found that we can observe the conductivity values between the grain boundaries, or these are just the boundaries of the radial junctions, and in between them the values are quite nicely homogeneous, so that allows us to assign a value to individual junctions. And to do that, we use the same image. We defined local areas. We did the averaging of the current from the local areas, and we could plot the histogram of the values. So the histogram of the measured currents from 0 value to minus 2.5 picoamps. So these would be the good diodes, the diodes which are in reverse and they have low conductivity, and these would be the bad guys which show the bad blocking behavior in the reverse direction. So that's the first part, but let us continue with other challenges, and we have to go fast through them. If you can measure the conductivity, you also want to define your illumination to measure the local photoresponse. We have done that for a longer time with microcrystalline silicon, and we have a problem there with the illumination of the experiment by the laser of the detection of the AFM cantilever. That scatters around the cantilever, and actually the conductivity maps correspond to the photoconductivity maps. We learned how to do the dark conductivity and photoconductivity maps. This is on microcrystalline silicon, not on radial junctions, but we see the dark conductivity and photoconductivity. They differ mainly by the values of the current, so the scale is about 100 times different here, but the character is mostly the same. And we also try to define the illumination by using the nose-type cantilevers, which allow the illumination to reach the sample surface nicely. But if we measure the photoresponse, we actually want to measure the photo IVs. So that means as we scan on the sample, at each point we want to measure the IV and to see what would be the conversion efficiency. And here we run in major problems. The small contact which is there available does not behave as a contact which we normally expect, and we are able to measure only basically in the reverse direction. If we go to forward direction, we have problems with local anodic oxidation, and we have to find ways how to prevent that, but that would be a subject of a different talk. If we are able to measure the local photoresponse, we also need to understand what is going on, and we started to do optical simulations. We don't want to really become experts like Miro because they have much longer tradition and so on, but we need to do different optical simulations than what is standardly being done. We understood that we need to simulate our probe in the experiment because it will change the experiment itself. We started with simple FDTD calculations, and so here this is for just one nanowire. We can do it for different wavelengths, and most importantly, we can do it for arrays of nanowires, including the scanning probe tip there. In this case, the probe tip was a perfect conductor. The size of the tip was maybe too large or too small, depends. But we see that it influences the absorption in this nanowire, and we need to do the calculations for the tip in all different positions. and that's quite intensive by the calculations. We actually do the simulations using a special machine which does not calculate using processors but using the graphical cards. Graphical cards are able to do the simulations in much better time than the normal computers, and because we need to do simulations in all positions, this is the only way how we can actually succeed. Now, you have seen that the nanowires are disordered and many things can change in them. So this is a small zoo of the disorder in the junctions. So we can see that some of them are shading each other, some of them are crossing each other. So the initial nanowires were growing close to each other, making a cross, then they were covered by absorber layer, and so we don't have a radial junction, we have a radial cross there. Some of them will be having kinks because the nanowire was growing up and then it changed direction. Some of them will be crowded together and you will also have empty spaces, and we need to find out what is going on, and that brought us to a need for correlating different microscopies. Oop. Yes. So I think I switched to another, I skipped one page, but that doesn't matter. We found out that we can do the correlation using a simple approach which resulted from an attempt to do the nanomechanical property measurements. We used the Fishersope Picodentor with a Vickers tip to indent our samples, and the indents are actually very small marks which are on the sample. This is an optical microscopy image with one of the top contacts, and we see the small marks here, here, and here. These small marks can be found by optical microscope, even so it's not really easy, and they can also be seen by other techniques. So by scanning electron microscope, for example, so this gives you a point to find out again the same position on the sample, and to do it by scanning electron microscope, which is interesting by itself, and in fact to do it also by another microscopy. So actually we can measure the same structure using the electron microscope and atomic force microscope. So we can correlate what is going on here with the electron microscopy and atomic force microscopy. We can do it even in optical microscope if you use the scanned confocal microscopy, and it allows you a number of possibilities. Actually, the experiment itself is already interesting, because if you do the indentation, you also clean your indenting tip, and you do it by indenting the PMMA. And we noticed that in PMMA we are having the radial junctions which were broken off by the indent itself. So the tip can be used as a way how to isolate individual radial junctions. And that opens a number of possibilities, and that brings me also to the conclusion just 1 minute before my time runs out. So let me summarize very quickly. I was showing you experiments on silicon nanowire-based cells. I discussed them in using concept of random diode arrays and the measurements of local properties by AFM. I have illustrated the topography and the conductivity images, which bring us to the distribution of local electronic properties, and hopefully it brings us on the way towards the microscopy of PV conversion. Thank you for your attention.
Thank you very much for your excellent talk.